Hello, everyone. My name is Yuesu Jin. I just joined ERL 1 month ago, and I will be the organizer of the fish in the next several cases. So if you have any suggestions, I'm happy to know. And just send me email or stop by my office and give me some suggestions. Okay, I'll start my talk right now. I will show some results I got from my PhD, and both on the experiment work and numerical modeling. And both of the work are supported by University of Houston rock physics lab and extract team led by my advisor Ying-Hai Zheng. And here is the outline. I did some experimental work from 2018 to 2021. That is a verification of the pressure surge effect by the low frequency laboratory experiment. That is my experimental work. And I also did some numerical work. That is using the 3D half-space boundary element modeling to do some research on the magma chamber vibration. So they are both related by the fluid inclusion. For the fluid field fracture, the fracture is filled with water, and that is can be regarded as a fluid inclusion in the elastic medium. And for the magma chamber vibration, the magma can be regarded as a fluid included within a rock body. So they are both related to the fluid in a elastic medium. And I'll first talk about my experimental work. So this work, the background or the motivation of this work start from the remote triggering of the seismicity. That is first observed by David Hill in 1993. And that is related to the Landers earthquake happened on the June 28th, 1992. And here is the epicenter of the Landers earthquake. And after they recorded recorded the triggered seismicity within the 10 days after the first shock and plotted on this map. You can see several clusters. And also David Hill plotted the stress perturbation distribution on this map. And several sites, including Geyser, Cascade, and the Yellowstone. These three sites, they are in the very low stress perturbation zone, but they still have the clustered seismicity triggered within 10 days after the first shock of the Landers earthquake. And all those three sites, they have the underground fluid reservoirs. And other observation also followed by David Hill on the trigger seismicity, including the some earthquake can be triggered by the very weak seismic perturbation dynamically. And after the earthquake, people observed the hydraulic change and the permeability enhancement. So, which means the seismic waves can permanently change the permeability of the formation. And
I think you can adjust the screen so it only shows your slide, because right now it's showing part of the audience.
You mean switch to the?
There's an option to not.
Layout. Change the layout.
Yeah, layout. Thank you.
Nothing changed. Okay.
There you go.
Okay.
Thank you.
And some Russians observed that when the train passing by the oil field, the vibration caused by the train can increase the oil production. And also seismic waves can cause soil liquefaction and multi-volcano eruption. And another study conducted by Brodowski and Prejean, they set up the seismometer on Long Valley, and they recorded the velocity change after 12 earthquakes from the Denali to Eureka aftershock. And only 3 earthquakes triggered the seismicity near the long valley because they put the seismometer on the long valley. That is Denali, Landers, and the Hector mines. But you can see for the Denali earthquake, the velocity, vertical velocity and the horizontal velocity is relatively lower than the North Ridge, Eureka Valley, and something like that. But all those cases with higher velocity perturbation didn't trigger the earthquake, but the Denali earthquake, Denali earthquake triggered the seismicity near Long Valley. So Brodowski did a low frequency filter on all 12 earthquakes, and they found Denali, Landers, and Hector mines. 3 of them both have a higher low frequency component in the seismic signals. So they proposed that the low frequency seismic signal is very important for the remote seismic triggering. So low frequency is very important. And from the observation, we now can have some basic thoughts. First is that the weak dynamic stress can trigger the earthquake remotely. And the fluid participation is very important from the Hill and the others observations. And the remote triggering has more sensitivity on low frequency signals. And currently we have several hypotheses to explain the remote triggering. First is the critical stress state, which means the lithosphere is already under the local lithosphere is already under the critical stress, and when the seismic wave passing by add the last part to trigger the earthquake. And another hypothesis added on the critical stress state is that the pore pressure plays a very important role in the seismic triggering, because the increase of the pore pressure can decrease the effective stress, which means the friction on the fault is decreased, and that might cause fault rupture. So David Hill and Brodowski, they both proposed some pore fluid increase mechanism, which can explain the fluid participation in the remote triggering. And we want to answer the third question, that how do the low frequency waves can change the pore fluid pressure, which means which can solve the third question, that why the remote triggering earthquake has a preference on low frequency incident waves. And in 2018, my advisor Yin Kaizheng, he proposed a new mechanism to explain the remote triggering, that is called a transient pressure surge effect in the fluid field fracture. He did a 2D boundary element modeling, and here is the modeling geometry. Here is the fluid that was set as water, and here is the elastic medium, and closed the fracture. And the incident wave source is placed in the fluid, and he tested in the frequency domain, do the frequency sweeping, and find the pressure amplitude within the fracture can be dynamically amplified to 40 times larger maximum. You can see here for example, when the incident wave frequency is 12 hertz to 16 hertz, the maximum amplitude is amplified to 40 times larger. And that is, according to the numerical simulation in 2D, that is caused by the slow wave or the Crockless wave in the fluid field fractures. The Crockless wave basically can be regarded as a two surface wave on the fluid solid boundary. And in the fracture, you have the two surface close to each other, and the surface wave coupled with each other to cause a very large amplitude surface wave. That is called a crack wave or Crockless wave. And he proposed the pressure surge effect. This hypothesis satisfies both the because it can amplify the fluid pressure. So maybe the low dynamic stress perturbation can be amplified and increase the pore pressure. And fluid participation is essential in this hypothesis. And that is sensitive to the low frequency signal because the amplification is frequency dependent. But the problem is that can we observe the pressure surge effect in lab or in field? So my first research topic is to design a low frequency laboratory experiment to verify the pressure surge effect. We have several challenges. The first is that we need a low frequency source, but in the laboratory, mostly we did the ultrasonic test. The transducer is working around the 100 kilohertz or above. But here, according to the 2D numerical simulation, we need the acoustic source frequency less than 100 hertz. And we need a large fracture model because if the fracture model is small, the Clark-Lewis wave is very weak, and we cannot observe the obvious amplification. And also, we need to measure the pressure variation within the fracture. So we need to place the sensor in the narrow space. So that means the commercial hydrophone cannot work. The diameter is too large to place it in the fracture. And thanks to the water tank left in the U of H Allied Geophysical Laboratory, we can do the underwater experiment. We just designed our low frequency system, including a low frequency source that can work from the 10 hertz to 100 hertz, and the fracture model built with two plexiglass blocks, and we insert some support between the two blocks to create the fracture space. And we install the 6 piezoelectric transducers on the upper block. The first one measured the incident wave pressure, and all the 5 transducers recorded the pressure variation in the fracture. And we close the fracture model. We close the 3 sides of the fracture model by the sound insulation rubber to segregate the noise, because this water tank is located in the basement of the building, and we have the water pipe and the AC system, so we have a very large noise. And
what's the dimensions?
The length is 3.8 meter of the water tank, and the width of the water tank is around 2.4, and the length of the fracture model is 1.2 meter, and the width of the fracture model is around 0.98 meter.
And the numerical model, can you go back to numerical model, please? So what's the dimension there? 1 meter?
The length is 8 meter, I think. The length is 8 meter. The length is 8 meter, and the aperture is 2 millimeter. You can see here.
What's the aperture of the experiment?
Experiment or numerical?
Experiment.
Experiment we varied for the 6 apertures because we cannot change the length of the model. The length of the model is fixed, but we can change the thickness of the support adding in the between the 2 blocks to change the aperture.
What were those length scales?
From 9.2 millimeter to 0.2 millimeter.
0.2 millimeters, 200 microns.
And we also set up some equipment, the electronic equipment to control the source and do the data collection. And here is a real pictures. That is a control equipment. And here is a water tank with a fracture model. And the source is hanging here. And that is the design of the source. That is a low frequency electromagnetic source. Basically, that is the same principle of the speaker design. And all the part is sealed in aluminum hull, and we just shake the membrane that is made by rubber, and this can radiate the low frequency wave. And we purchased the commercial hydrophone to do the benchmark. or to do the validation. And that is the waveform and the spectrum recorded when the source working at 10 hertz, 20 hertz, 30 hertz, and 40 hertz. And you can see from here, we have some small peaks. They are the noise, background noise of the building AC system and the pipe system. We cannot remove it because the water tank has a very strong coupling with the land. And that is the design of the transducers. The design is contributed by my collaborator, Nikolai Dior, and he designed this airbag, the piezoelectric sensor, which uses the flexural mode of the PZT film, which can have the higher sensitivity than the compression mode of the PZT.
They can feel 30 hertz, the piezo sensors. This sensor can feel like 10 hertz.
Because we use the flexural mode. The flexural mode can work in the low frequency. Yeah, we try to directly attach the PZT film on the surface, but it cannot sense the low frequency wave.
So don't they use spec sensors?
We should repeat the question because it won't get picked up. It's a good question. Just repeat it for the people on Zoom.
Oh, okay. The question is that how the PZT sensor can detect the low frequency wave. Is my question?
Yeah.
Yeah. The answer is that we set up the airbag, the air cavity, which means we can excite the flexural mode of the PZT film. The flexural mode works in a much lower frequency, so it can for the low frequency, the flexural mode can be used to detect the vibration. I will show the waveform recorded by the PZT in the next slide. And this one is okay. This one is an upper block installed with 6 transducers. This one P1 is a transducer measuring the instant wave, and we have 5 transducers to measure the pressure change in the fracture. And we also tested with our low frequency source and using the bubble, the air bubble in the water tank. And here is the recorded waveform both by the commercial hydrophone and our transducers. You can see our transducer can capture the low frequency signal well, but for the high frequency oscillation, the flexural mode cannot work. And that is a validation using our low frequency source. This is a source working in the 10 hertz, and this is source working in the 30 hertz. And here you can see that is the noise.
What's the natural frequency of the membrane?
It's sorry, I forgot. I got the information from the provider, but I forgot. I did it 3 years ago.
Quick question. Why the building signal shows differently at different frequencies?
You mean all the 3 peaks, several peaks?
Yeah.
We measured for several times, and every day before we start the experiment, we'll measure the building signals. It always change. I don't know why, but we have 3 peaks. First is 18.4. That is the largest peak, always exists, and some peaks around the 30 hertz, and the low frequency signal always shifted from the 0.some hertz to 10 some hertz. It's always
you tried to characterize the building, but it was changing all the time.
It's changing because the AC and the pipe system, and when somebody switch off and switch on the pipe, it will generate a different type of noise. So that is the
sensors. Because 30 hertz is like a human ears, I don't know, some microphone, correct me,
yes, I can hear the low frequency. It's like it's like that. Yes, I can hear, and we also use the memes the MEMS is a very small microphone used in your phone, and we purchased the MEMS and attach it at a different place in our lab. All received the low frequency vibration, but we cannot eliminate the vibration, so we just left it. And here is a picture I took in the side view of the water tank. We have the side window on the water tank, and that is the upper block, and that is the down block, and here is the front view, and we have the source hanging here. And basically, that is our measuring geometry. And before we start the test, we also do the calibration or benchmark of all the 6 transducers to bring it in the same response level, because we need to compare the data measured by different the different receivers. So we need to we just use the same commercial hydrophone to calibrate all the 6 transducers. And in this experiment, we changed the aperture from the 0.2 millimeter to 0.2 millimeter. And to quantify how much pressure is amplified in the fracture, we define the pressure surge factor. That is the pressure measured in the fracture to the incident wave pressure. And here is the pressure surge factor in the frequency domain. We did a single frequency sweeping and get the maximum amplitude. Do the ratio of the H1 to H5, that is the sensor in the fracture, to the P1, that is the sensor outside of the model to measure the incident wave. We do the spectrum ratio, and because of the problem of the projector, so this figure on the screen has a very low resolution. I will show the zoomed in figure in the next slide. And when the fracture thickness or the fracture aperture is 0.95 millimeter, we observe the maximum amplification at the hydrophone 4. And when the frequency is 29 hertz, we achieve the maximum amplification is 25.2. And here is a zoomed in figure of the when the fracture aperture is 0.95 millimeter. You can see here we have the very large amplification. But for the third hydrophone H3, we cannot observe observation. We cannot observe the amplification.
So 3 is right in the middle.
3 is in the middle.
And 5 is at the end. So
yes.
So it's like a flute, like you're seeing the end.
It's a standing wave.
It is, yeah.
It's a standing wave. So 5 is close to the end of the fracture, and 3 is in the middle. And the first one, the H1 is close to the mouth of the fracture.
You're not activating the full mode. It's the first overtone.
Yes, that's the first overtone. I don't know why the amplification is maximum in the first overtone. Maybe we excited the base mode, but no very large, very good observation is observed.
Is it related to resonance frequency?
Yes, that's a resonance.
Because the PMMA we use, right, is PMMA polymer, right?
And
the plate you use is a PMMA, it's a polymer.
PMM
Plexiglass.
plexiglass.
Yeah.
That's plexiglass.
So that would be the resonance of the whole, whole block. This is 1 meter, and if you assume your speed is 1,000 something meters per second, this is going to get you, I don't know, some sort of resonance frequency.
That's not the resonance of the block, because that's a resonance of the Crockless wave, the surface wave in the fracture. So when that wave forms the standing wave, we have the amplification, because we also measured we put the transducer on the surface of the plastic glass. We cannot observe any signals. So the vibration of the plastic glass is very small. And here I show the waveform when the maximum amplification happened, 29 hertz, and the fracture aperture is at 0.95 millimeter, and from H1 to H5. And here you can see the orange line, that is the incident wave, and the blue line is a wave measured in the fracture. And you can see the pressure is amplified. And what's meaning of the pressure amplification? What can we infer from that observation? If we have the stack of coin of the 40 quarters, that will cause the 4 kilopascal on the table. And if that is amplified by the pressure surge factor observed in our experiment, we will have the 100 kilopascal level of the stress change. And that is enough to trigger the volcano eruption. So this figure is got from the one GRL paper, and he did the observation of the volcano triggered by some seismic events related to the epicenter distance. And for the certain type of the volcano, the stress perturbation less than 100 kilopascal can trigger the eruption. And I also wrote my full space boundary element code to do the 3D simulation. My advisor did the 2D, and I did the 3D. And but that is limited by the algorithm, because my algorithm is really primitive, so it cannot deal with dense mesh. And that is a geometry. I did the same setup as my advisor did in his paper. The source is placed in the Fourier domain, and I place the receiver in the fracture to measure the pressure change. And here is some preliminary result. We have the 4 apertures from 1 centimeter to 10 centimeter, and the fracture length from the 1 meter to 4 meter. And when the fracture aperture is too large, the wave cannot form the quarkless wave. So you can see the dispersion is like the very flat dispersion. But when we make the two side of the fracture close enough, the similar resonance can be observed. And even in the 3D, it has a higher amplification factor. And for some cases, we can observe the wave node. Such as this, we have the sending wave, and you can see the wave node. And in the middle, in the between of the two nodes, the pressure is amplified. So
do you know why the node is only the nodes are only observable in some cases? Like, is the node at the top in the other cases?
I think that excites different modes.
Higher frequency.
Yeah, it's in the higher frequency. For this one, it's 90 hertz, because I have the relatively smaller peak, but in the color bar, it is smooth. You cannot see it on the color map. So only the amplified maximum amplification peak you can see.
And you had to do different dimensions for the numerical study than the actual lab experiment. But can you relate the numerical results to the experimental results in, I don't know, some ratio or something?
No.
I qualitatively agree.
That's only qualitatively. I tried to link them by some 1D modeling, but even the 1D modeling cannot give the correct result both on the numerical and oh my, it's not.
What frequency is that?
The noise frequency, or I don't know.
These have different incident waves. What are the frequencies that you're using?
Oh, I did it in the frequency domain. So that is the frequency sweeping single. The frequency interval is 0.2 hertz. I think 0.2 or 0.1 hertz.
So what's the, this is the range of frequencies you see there?
I just sweep from the 0.2 to 100 hertz, and the interval is 0.2, 0.2. Yeah. And for the 3D simulation, we also observe the amplification because we first find that when the fracture aperture is too large, we cannot have a very good amplification. So that means the amplification comes from the Crockley's wave, which means you need to couple the surface wave of the two surface to form the resonance. And the geometry is important. The geometry need to hold the resonance or standing wave in the fracture. And it has a frequency dependency. You can see the peak does not appear randomly. It has some distribution. So that is the frequency dependency. And that is my some summary on my experimental work. We proposed a new dynamical triggering mechanism that is called the pressure surge effect. And the slow wave in the fluid field fractures plays a very important role in the PS effect. And we designed a low frequency underwater experiment to verify the existence of the pressure surge effect. And we achieved the maximum 25.2 amplification factor.
If the fracture aperture was closed at the end that was closer to the source, so it was a fully closed fracture, would you still get this effect?
Can we repeat the question?
So if your fracture was completely closed.
You mean I even close the near side of the fracture?
Right, and the energy is transmitted from the fluid into the plexiglass and then back into the fluid.
Oh, we can. We did it. We did it. We cannot observe because we close the fracture by the sound insulation strip, so the acoustic wave cannot penetrate. Only the acoustic to the elastic, elastic to the acoustic. The incidence wave is too small, and we cannot.
So it is already effectively closed.
No, he's saying that if he closes it, there's too much attenuation, doesn't get through.
Right, right.
He close it with
The four sides. We also did the test to close the four sides of the fracture to make the fracture fully separate from the outside water tank, and the power the instant power is too small, so we cannot. Maybe there is a amplification, but we cannot measure. The sensitivity of the sensor is cannot detect.
How would this translate to a field scale? Let's say you're arguing that this could be a mechanism for earthquake, but as a subsurface, you don't have a water pool that have wave generation in there and sent to fractions. It's all big solid with fluids and fractures. And the seismic waves, they come from far.
Mm.
It's a couple of fluids and rocks together, as you were saying. So how would that translate to that case?
Yinghai had another student. He's working on this. Start from this one. So I only did the first stage, and to apply it or to put it in the context of the field work, that is the second, even the third stage. And we need more people involved in the research. Now we have one new student. He's very good at multi-phase flow simulation, and he is currently doing the more complicated simulation and related to the field.
But in the lab, if you have tried to use a thinner plexiglass, maybe try to apply the waves to the plexiglass, then it gets transmitted. That was not tested, right?
Yeah.
I didn't do that because the funding supported for this research only can afford the two sides of the plexiglass, and after that, the Yinghai hadn't got any funding from the NSF or DOE. So now the students just supported by another funding from the geothermal project. But his research topic is following my study.
So can I ask a question about the this pressure surge effect? Can you hear me there?
Yeah, barely, Brad, speak up.
Actually.
Okay, great. So as I understand it, you need to have this standing wave criteria so that there's a standing wave inside your fracture, which makes sense in your plexiglass experiment. Excuse me. But my view of fractures is that they're very rough. And so would you expect a standing wave in a rough fracture?
Let me think about this. I'm not sure. I'm not sure what happened if we have the rough fracture, because the rough fracture will cause attenuation, very strong attenuation. So now the fracture surface is very smooth. The channel for the fluid is very clear. So we can observe the good amplification. But for the rough fracture and some inclusion field in that, I think the case will be much more complicated, and I have no idea what will happen for that type of the fracture.
Thank you.
Okay, thank you.
This reminds me, it's kind of like why the tides are so big in the Bay of Fundy, because the natural frequency of the Bay of Fundy is 12 hours. So there's a pressure amplification from the tides in the ocean, amplify the pressure in the water in the far end of the bay, and that's why the tides are 10 times higher than the ocean.
Do you know Chi Wang? Chi Wang, he worked in the UC San Diego. He did the research on the tide amplified the water level change in the well, and he also had some research, published some research on review of geophysics on the water level change. And some Chinese scholars, they observed that the pressure drastically increased after the Wenchuan earthquake. China had a very large earthquake at Wenchuan, Sichuan, and some water level, some water well in Fujian province, very far from the Sichuan, but observed the very strong fluctuation of the water level. Yeah.
I think that's unrelated. You're talking about the focusing, the amplification of the day.
Yeah, I was thinking more of the modes, why you have the highest mode at the far end of the pipe, the forcing. That's focusing. That's dimension. That's focusing. That's the magnifier. Where is activity? There, I know, but the Bay of Fundy, because natural frequency is the same. It's the whole day. You just see it more strongly.
Okay, I'll move on to the numerical part. The reason why I did the numerical part, because I failed in the simulation of the you can see from my previous simulation, I just stopped at 1 centimeter aperture. That is the maximum aperture of our experiment, because when I shrink the aperture, I failed to get the reasonable result. It gives the random waveforms. So that is some algorithm problem. I cannot handle it in the short time. So I switched from the full space boundary element modeling on the pressure amplification to the volcano seismology, because both of them share the same point that related with the wave propagation in the elastic medium with fluid inclusion. And for the background, that is related to the long period, long duration events observed near the volcano. You can see from this figure, that is a seismogram recorded near the volcano Cotopaxi volcano, Ecuador. And this seismic signal duration is very long, to the 45 second. And here's the spectrum of the signal. You can observe the dominant frequency that is in the very low frequency. And this type of the long period, long duration event is believed related to the vibration of the magma chamber. So if we have the very large volume of the magma and the wave in the magma resonance back and forth can radiate such a type of the low frequency. Several models proposed by Bernard-Schmidt, they do the frequency fitting of the low frequency signals, and they thought that can explain the problem. And my motivation is that the magma can be regarded as a homogeneous medium, and for the resonance problem, the boundary geometry is very important. So for Bernard-Schmidt, they just adopted the spherical model or the crack model. That is a very simple geometry. But if we have the complicated geometry, we need a more dedicated numerical tools. And the boundary element is a perfect tool because it's focused on the boundary geometry. And my point is that after we add the half space, the free surface, how much influence of the free surface caused to the resonance of the magma chamber. So here is the basic physics of that problem. We have the free surface, and we have the background rock formation, and we have the magma chamber inclusion, and we added a source. So first we can observe the direct arrivals and some resonance in the magma chamber. But after the free surface is added to the geometry, we have the surface multiple and the surface waves. So all those waves, they come together. And for the full space boundary elements, I can only handle the direct arrivals and the reverberation. But for the multiple reflection and the surface wave, I need to either add the free surface as a new boundary in, which means we need to the mesh number, the degree of freedom is will be increased, and or I can find some way to directly calculate the half space Green's function, and in the half space Green's function, the free surface effect is already included, and that is a basic equation of motion for the fluid elastic coupling for the boundary element. And with the boundary condition, finally, we can convert the boundary integral equation to the linear algebra problem. And when we add the free surface, actually, we just need to replace the traction Green's function and the displacement Green's function in the elastic body by the half space traction Green's function and the half space Green's function. But the problem is that the analytical solution can be get for the full space Green's function, but for the half space, we have no analytical solution. We can do it either by Carpenter the hook method, that is for the time domain, or we do the wave number domain integral, that is for the frequency domain. In my half space boundary element, I conducted a wave number domain integral, that is for the frequency domain. And another problem is that when you do the boundary element calculation, the Green's function has a singularity. You need to deal with the singularity. And for the analytical form, we have the singularity, we have the regularization algorithm. But for the half space boundary element, the problem is that the Green's function is represented by the integral. The singularity is a fast oscillation component of the Bessel function. And I just do some mathematics, find some terms. That is a highly oscillation. Those terms comes from the contribution of the direct arrivals. And fortunately, the direct arrivals of the half space, that is the same wave, S wave and the P wave in the full space. So that is replaced by the full space Green's function, which has an analytical form. And for other part, surface wave and the multiples, they can be calculated by the wave number integral without divergence. So basically, the half space Green's function and the traction Green's function can be decomposed into two parts. One part is one part is the analytical full space Green's function, and another part include the surface wave and the multiples, and this can be calculated by the wave number integral. And I did the benchmark. I placed the magma chamber very deep and placed the receiver near the magma chamber. So the reflection and the surface wave cannot influence the observation point. So in this way, I can compare the half space result with the full space because the reflection is very weak. And from the three components, we can see the half space boundary element fit well with full space, so which means our algorithm works well. And here is the modeling geometry to study the magma chamber vibration. I put the receiver or the seismometer on the surface with an epicenter distance from 5 kilometers to 40 kilometers. And I put the magma chamber below the surface. And here is the geometry of the magma chamber. I selected the ellipsoid shape of the magma chamber with the horizontal two axes equal. And I only changed the vertical axis. So we have the short-long axis ratio as a characteristic parameter for the geometry. And here I show some waveform. This one is a short-long axis ratio is 0.6, and the depth of the magma chamber is 2 kilometers and 3 kilometers. You can see from all the waveforms are normalized. So you can see from the when the depth is 2 kilometers, we have with the half space, we have a much longer oscillation than the full space. So which means the free surface plays a very important role to feed back part of the energy back to the magma chamber to endure the oscillation. And for the 3 kilometers, because of the geometric spreading and the some mismatch of the frequency, the half space pace and the full space, they have the similar oscillation period. And here is the spectrum analysis when the epicenter distance is 5 kilometers. And you can see for the half space, we have a new peak. We have the new peaks. And the black line, that is the full space boundary element, represents the natural frequency of the magma chamber. But when we added the free surface, the resonance frequency shifted to a lower frequency and has a higher amplitude. And that is a wave number, that is a waveform when the short-long axis ratio is 0.2 and the depth is 2 kilometers and 3 kilometers. And we can see the same thing with the help of the half space. The oscillation of the magma chamber endured much longer than the case without half space, without free surface. And here is the spectrum. From both of the case, we can see the low frequency component added to the waveform. So based on those observations, we think we can regard the free surface as a reflection mirror in the we can take the analogy of the laser system. The laser system, we have the resonance chamber and we have the reflection mirror, and the reflection mirror can feed back the energy back to the resonance chamber, which can amplify the amplitude of the light. So the similar thing, we have the free surface and can feed back the energy back to the magma chamber, which can make the vibration longer and stronger.
So let's read through this.
Okay. So that is what we found by the half space boundary element modeling.
Okay.
And that is summary. I developed the half space boundary element code and give the regularization of the wave number domain integral. And that is validated by the full space boundary element code I had. And found that with the free surface, with the help of the free surface, the long duration signal can be enhanced greatly. So that is my colleagues, my advisor, Ning Haizheng. He did a postdoc at ERL for 7 years from 2007 to 2014, I think. And Nikolai Deyor, he instructed me on the laboratory experiment, and he had a design of the low frequency sensor using the fractal mode to detect the low frequency wave, and that was me. Yeah. And the experiment work is supported by NSF. Yeah, that's all. Thank you for your time and attention.
Good. So, question.
I'm just curious, as the epicentral distance gotten smaller, your amplitude was increasing. You didn't show the result at 0. So what happens directly above the magma chamber?
Oh, the reason why I intentionally make the distance because we don't know it's very hard to directly set up the seismometer above the seismic wave, above the earthquake location. So I just make the distance. And if I put the seismometer above the epicenter, above the earthquake location, the much stronger oscillation can be observed. But I didn't show on the figure because usually we cannot set up the station directly on the earthquake location. But the waveform is similar. The interesting is that when you increase the epicenter distance, the surface wave dominate the contribution, and that cannot be modeled by full space boundary element. So for the full space boundary element, all the signal comes from the magma chamber vibration. But if we add the free surface, the surface wave not only surface wave usually has a larger amplitude than the body wave, but it not only has a larger amplitude, carries more energy, but it also represents the longer duration oscillation of the magma chamber. So both the energy feedback from the free surface to the magma chamber and the magma chamber vibration also feedback more energy to the surface wave.
Thanks. Are there other questions about the numerical part? Can you show the spectra again? So it went by a bit too quickly. I saw. So in this one, the peaks are aligned. Are they always aligned, or was that different before? Go to the previous spectrum.
They're separate, actually.
Okay, so tell us again what was the change between these two slides that made the
black line, that is a full space. The result of the full space boundary element represents the natural resonance frequency of the magma chamber. But when we add the free surface, the wave will go back to the free surface and reflect it back. That will form another resonance series. So it introduced some low frequency component. And when the low frequency peaks match with the natural frequency, that will cause the enhanced vibration. But for this one, the depth is 3 kilometers. The depth is 3 kilometers. We have a very weak enhancement. And in the same time, on the spectrum, actually the low frequency peak caused by the free surface reflection has a smaller match area with natural frequency. So because those two waves cannot match, so they cannot form the beating. With no beating, we have a very short period of the resonance.
So everything you explained can apply to this slide by itself. Is that right? But I want to understand the difference between this slide and 2 slides later when everything is aligned. What changed?
Yeah, everything can be shown on this slide. Actually, for this one,
The sign, the ratio.
the ratio, yeah, the ratio of the magma chamber.
Changed.
Yeah, C changed. The C represents the short long axis ratio. the short axis.
Okay, so you change the aspect ratio. It's
Yes,
made
of
it
the
flatter or taller?
make it flatter.
And show that spectra?
And you can still see the low frequency component for the 3 kilometer, but because of the resonance peak, resonance frequency of the magma chamber also changed to the shift to the lower frequency. So they still have the some match. So
Okay.
for the
And what about the depth of the epicenter? If it was further from the free surface, does that have enough, must affect the frequency or not? That's what this shows, the epicenter distance. That's the gray path distance.
that's a projected distance. Projected the source on the surface, and just to pick a line
Okay,
and
so
set up the.
And does that not affect the frequency very much? It just affects the power,
It's
the resonance frequency.
it also has an impact on the resonance frequency. You can see here with a larger epicenter distance, the surface will dominate the signal, and that will change the spectrum. I only show the spectrum of the 5 kilometer, but if you shift if you go further, the spectrum will also change accordingly.
Good.
So quick question, when you change the aspect ratio from 0.6 to 0.2, as Amy was saying, the richness of the spectrum changes quite a bit. In the case of the smaller aspect ratio, it's not actually changed. The high aspect, I guess this is the low aspect ratio. There's a lot more of oscillations. Why do you get that?
Oh, I normalized the waveform for one aspect ratio, so they cannot directly compare for the of the waveform of the case with different aspect ratios. Actually, for this one,
Like here, yeah.
this one has a much stronger oscillation than that one. But because I do the normalization, so I have to show them I have to show 4 traces in one figure. And if I use if I use a normalization factor in previous slides, this one will occupy the whole.
No, but I'm talking about the spectrum.
Spectrum.
Yeah, let's say here, we don't see lots of high amplitude fluctuations. In this case, when you go to 0.6, you see a lot more of that.
Oh, yes.
If you go to the 0.6, yeah, here.
Yes,
So
here
yeah,
we have a lot of
up and down, yeah.
At low frequencies.
At all frequencies.
at all frequencies. Yes. Actually, I calculated from the 1 to 0.2, and some of them have such type of the oscillation.
So is that spurious effect, or is it real in the magma chamber?
I think that comes from the reflection from the free surface, because on the black line, that is calculated by the full space boundary element, which represents the natural frequency of the ellipsoid. So that is very smooth, because here it is smooth. But after I add the free surface, the spectrum becomes much more weaker.
So the half space is the blue one.
Yeah, half space is the blue one.
I'm suspicious that it's spurious, just because it's alternating. I mean, the fact that well, actually, these are, if you plotted the points, then maybe we'd see a couple of points, then it goes down, a couple of points up, then it goes down. I would try to do a conversion study if you did this again, but it's okay.
Have you done any tests on energy conservation for these plots? Those are physical.
Oh, for energy conservation, you mean consider the geometric spreading, the summation of the wave energy in the epicenter distance.
When you compare extinction with scattering, you should.
Oh, I didn't do that test. I only the backtrack test that I did is just this one.
compare extinction and scattering, so what do you mean exactly?
So if.
What would you calculate?
I assume you have no absorption. So your model is purely elastic.
Pure elastic, no
So
attenuation.
extinction of it should be equal to scattering.
So something like add up the energy around the outside of the domain
Yes,
and compare it to what?
to the scattering energy. So if your error is 0, then you can be sure your model is convergent.
So the scattering energy, you mean like do a volume around the source? So I add up the energy.
Total energy, not local energy. You take the whole energy that is scattered from the sphere or from your ellipsoid at a particular radius, and you take the extinction also of the same area, and you compare the two.
What is the extension?
So the formula of the extinction is the interaction of the incident and scattered field twice. And the scattering is it's the interaction of the scattered field squared. So PI, or you use your attractions, right? So the traction is incident field times the scattered field. So that gives you one component of extinction. And for the scattering, you take that squared, TS squared.
Yeah, I think I see. It's like I can't figure it out.
Actually, I did the two benchmark. This is a benchmark of the half space, but this is the benchmark for the half space, and with my full space boundary element code. But I also did the normal mode summation, the pure spherical normal mode summation to test my full space boundary element. I didn't show here, but I showed in my defense slides. I use a normal mode summation, or I change the different because you can play with it with a KVT, or add some inclusion, or just the free surface of the free oscillation of the sphere. I tested several cases by the normal summation and compared the result with my full space boundary element code. That is a benchmark of my full space boundary element code. And after that, I use my full space boundary element code to benchmark my half space boundary element code. So here I just show the benchmark by my full space boundary element code. But my full space boundary element code also was benchmarked by normal mode summation.
So you have some sort of validation.
Yeah. Because actually I had a lot of numerical issue during when I wrote.
So the resonances that Jean was mentioning, those could be more like modes because you're doubling the volume.
Oh yes.
Right, so you're doubling the volume, so you increase the number of resonances.
Yes. I didn't. The volume of the magma chamber changed. Yes, and that may introduce more complexities of the resonance. Yes.
Question. For the magma chamber, the boundary also serve as an interface for a wave reflection.
Yes.
Those reflection cause the fluctuations in the when the aspirations.
You mean the boundary of the magma chamber?
Yes, it can reflect the waves.
That is already included in the full space boundary element. For the full space boundary element, I only consider the infinite large elastic medium.
For the half space case, when the wave goes down and hit your magma chamber again, and then the wave can reflect back towards the magma chamber and result in the fluctuation.
Yes. Everything is included in the half space boundary element, and the wave bounce and back between the magma chamber and the free surface forms the.
Yeah, I mean, is that a possible reason which can explain the fluctuations overall?
Yes. That is a very important contribution for this part. But I cannot say why for the this short long axis ratio we have the very strong oscillation, but for this one we have the relatively smooth oscillation.
Because the shape of magma
Yeah,
chamber influence the reflection. I don't know exactly how it will influence, but I guess there might be.
Yeah. Yes, might be, but I cannot tell the exact reason either.
There's actually two more questions about the experimental part, which I'll read out. To what degree does the source need to be aligned with the fracture to get the surge effect? I think he means if I move the source off the line of the axis, the long axis of your fracture, does that have an effect? Do you know?
Oh, we did it. We did the test. Still, we can observe the amplification, but the amplification, the pattern. Okay. The pattern changed. The amplification factor changed. It cannot be well understood by the standing wave because cannot be. Because the instant wave, the angle of the instant wave changed, and the input power also modified.
He also wants to know if you tilt one of the blocks so that the aperture is larger at one end and smaller at the other end.
Oh, we thought after we finished the experiment, we have more thought on that, but we didn't do any test on it because we borrowed the water tank from the AGL, and they also had their own research schedule. After we closed the experiment, we totally return everything back to the AGL, and we cannot do the experiments anymore.
I had I think we run some simulations on that. The amplification is much stronger. That's what I remember. The aperture is increasing. That's the highest apparently at the tip. And that was one of the arguments, conceptually speaking, of increases stresses at the tip of fractures that would allow further propagation.
Interesting. Okay, well, we had a lot of good questions before, so let's thank our speaker again. And
Thank you.
keep your eye out for, I think there's going to be a fish in 2 weeks, correct?
Yeah, October 20th. October 20th.
You know about that.
Did you have to stop the Zoom?
Yes, I stopped the Zoom.
Good.
Quick question. Yeah. Is it possible to use pressure search to increase permeability? Like how
To do what to increase?
increase permeability
Using
pressure search. So low
pressure.
frequency
Oh, okay,
search.
yeah. Yeah, let's discuss that. I mean, tracking does that. So in tracking, you inject a fluid, and then if there are existing cracks, then if the fluid gets into the cracks, then the increasing pressure can expand the crack.
Yeah.
A lot of studies of that.
But in
So
this
yeah,
case, I mean,
one of the
This is different. This is more of just a resonance effect.
yeah.
the fracture
I
has
understand.
its
But let's say there is already a fracture.
Yeah.
and then you're exciting the waves in
It's
a
hard to
water
compare with
tank.
oil.
So one of the ideas of studying each eye is to see
And
if they can try
with
to
the
decide
source, make
solid and use the solid
change the
complex
wettability.
to see if
Maybe
there's any
it's
effect. That's where you have.
always.
Mhm.
And the permeability of water as well.
Now, the fracture aperture radical is the question of mine, that's
And
great.
let's say we
And
have
the waves coming in.
well, for the search, is it possible to change the wettability?
The raw factor will.
Well, mess it up. But in the field, you've got.
So the
very small
wettability
fractures. So in the
what
lab,
is it
you did
depend
200 microns, is that the smallest?
Yeah,
that is.
It's a property of the interface
Yeah.
between the
No,
fluids.
it's